So, what is natural refrigerant? Natural refrigerant have been essential to the food processing, storage and delivery infrastructure of our economy. More recently, natural refrigerant technologies have enabled refrigeration system to be used for air conditioning in publicly accessed buildings, increasing output efficiencies for power generation facilities and emissions control for various industries. Next, I will discuss about the transformative potential of natural refrigerant in enhancing human comfort and ensuring food safety. So firstly, natural refrigerants such as carbon dioxide, ammonia and hydrocarbon offer significant environmental benefits. They have low or zero ozone depletion potential and minimal global warming potential compared to synthetic refrigerant, and this makes them eco-friendly choice in combating climate change. Next, for energy efficiency, beyond their environmental advantage, natural refrigerant contribute to enhanced energy efficiency. Carbon dioxide systems, for instance, are not for their efficiency in various climates. This translates to lower energy costs and reduced carbon footprint, aligning with sustainability goals. For improving human comfort, in terms of human comfort, carbon dioxide-based air conditioning system provide effective cooling while consuming less energy. This not only ensure a comfortable indoor environment, but also reduce operating costs for homeowners and business alike. Next, for safeguarding food, when it comes to food safety, natural refrigerant like ammonia play a crucial role. Ammonia is widely used in industrial refrigeration due to its efficient cooling properties and proven safety required in food processing and storage facilities. So lastly, for regulatory landscape, supportive regulations are increasingly favoring the adoption of natural refrigerant. Governments and international bodies are incentivizing their use to meet environmental targets, ensuring compliance and driving innovations in refrigerant technologies.
Today, I would like to talk about why carbon dioxide or CO2, also known as R744, is the most promising refrigerant for the future. As we move towards more sustainable and environmentally friendly solutions, CO2 stands out due to its unique properties and benefits. I'll also discuss the areas where CO2 is particularly well suited for the application. First, let's consider the key advantages of CO2 as a refrigerant. The first point is environmental impact. CO2 has a global warming potential of 1, which is the baseline of all refrigerants. This makes it an extremely environmentally friendly option compared to traditional hydrofluorocarbons, which have much higher GWPs. Additionally, CO2 has an ozone depletion potential of 0. It does not contribute to the depletion of the ozone layer, further enhancing its environmental credentials. The fourth point is regulatory compliance. As global regulations aim to reduce greenhouse gas emissions and phase down high GWP refrigerants, CO2 naturally complies with these standards, making it a future-proof choice. Now let's explore the specific areas where CO2 is particularly well suited. First, industrial refrigeration. In large-scale industrial refrigeration, carbon dioxide is increasingly recognized for its efficiency and safety profile, making it an attractive choice for various applications such as food processing, cold storage, and ice rinks. Here are some key points explaining why CO2 is advantageous in these settings. For efficiency, I will explain this in terms of thermodynamic properties. High volumetric cooling capacity. CO2 has a high volumetric cooling capacity, which means it can absorb a significant amount of heat per unit volume. This allows for the design of compact and efficient refrigerant systems. Next, low energy consumption. Due to its efficient heat transfer properties, CO2 systems often require less energy compared to traditional refrigerants. This can lead to significant operational cost savings. Next, low energy consumption. Due to its efficient heat transfer properties, CO2 systems often require less energy compared to traditional refrigerants. This can lead to significant operational cost savings. CO2 in air conditioning. While CO2 is well established in industrial refrigeration, its use in air conditioning system is a newer and developing area. Here are key points that elaborate on the potential and ongoing developments of CO2 in air conditioning. Potential of CO2 in air conditioning. In terms of thermodynamic advantages, high heat transfer coefficient. CO2 has excellent heat transfer properties, making it highly effective in both heating and cooling applications. This can lead to more efficient and compact AC system designs. Second, wide temperature range. CO2 can operate effectively over a broad range of temperatures, making it suitable for various climatic conditions.
Next, I want to talk about the benefit of using CO2 or carbon dioxide R744 for the most promising refrigerants. For the first is low environmental impact. Low environmental impact can help reduce the carbon footprints, enhancing their reputation and their sustainability. For the second is high energy efficiency. High energy efficiency is not only conserved for resource but also ensures sustainability, long-term service in operating costs. For the third is longer equipment life. Longer equipment life can improving the energy efficiency in refrigerants equipment not only reduce operational costs but also extending the service life of the equipment, thereby enhancing the sustainability effort and minimizing environmental impact of the long time. For the last is better temperature control. Better temperature control is not only provide more precise of regulation of the temperature, but also enhance the quality and longevity of store product, ensuring optimal condition for prevention and reducing waste.
Now we're going to discuss about safety of natural refrigerant. The risks associated with the use of refrigerant can include toxicity, flammability, asphyxiation, which is breathing difficulties, and also physical hazard. Aspects that may represent a safety risk. The first one is ammonia. Ammonia is toxic and can be very harmful if we inhale. While not highly flammable, ammonia can be explosive in high concentration when it mixes with air. Second one is carbon dioxide, CO2. In high concentration, CO2 can displace oxygen and pose a risk of asphyxiation in enclosed space. Carbon dioxide, CO2, become less efficient as a refrigerant in high ambient temperature. The last one is propane. Propane, which is hydrocarbon, are highly flammable when mixed with air. Next is about limitation and mitigating risk. For limitation of ammonia, due to its toxicity and corrosiveness, ammonia is mainly used in industrial application and large scale of refrigerant system. And then for carbon dioxide, CO2 system can be less efficient in high ambient temperature, impacting their performance in warmer climate. And then for propane, due to its flammability, there are strict regulations limiting the amount of hydrocarbon refrigerant that can be used in certain applications. And then for mitigating risk, for the ammonia, we can implement a leak detection system and adequate ventilation. And then for carbon dioxide, we can design a system to handle high pressure safely. And last one for propane. Propane, we can use flame retardant equipment and implement strict safety protocols.
Here are some examples of natural refrigerant costs in the market. Ammonia R717. Ammonia is commonly used in industrial refrigeration. The price can vary between $2 and $4 per kilogram, but it may differ depending on the region and supplier. Number 2, carbon dioxide R744. CO2 is used in various applications including commercial refrigeration and heat pumps. The cost is generally around $1 to $2 per kilogram. The third one, propane R290. Propane is used in residential and light commercial refrigeration. The price is typically between $1 and $3 per kilogram. In conclusion, the prices provided are approximate and subject to fluctuation due to market conditions, supply chain dynamics, and other economic factors.